Sure.
Okay, hello everyone. Welcome to the third session of our quantum computing workshop. From today until Friday, the lectures will be conducted by Krzysztof Kuba. And yeah, I think we can start. So, Krzysztof, if you are ready, the Zoom is yours.
Yeah, sure. So yeah, hi everyone. My name is Krzysztof, and then as I said at the beginning of the workshop, I'm delivering this workshop as collaboration with FinQubit. And let me know if yeah, in the meantime, you can log into the FinQubit platform because as we are 23 participants, it may take a while for you to load the environment. But yeah, so today we're going to start a new programming language, which is Cirq. And this is language, quantum computing language provided by Google. And we will also start and remind ourselves about Grover's algorithm. So quite a lot of stuff to do, but the Grover algorithm will then be used to find solutions for the Max-Cut problem, which we will cover tomorrow, the graphs and how this problem works, and we will also learn about how to add numbers on quantum computer. And on Friday, we will actually switch also to Julia, and I will show you how you can implement the Grover's algorithm for the max-cut problem. And we will combining all those blocks that we're going to learn today, so the Grover algorithm, and tomorrow's number adding, to finally solve the max-cut problem with Grover's algorithm on Friday. So yeah, do you have maybe any questions before we start? Any problems, issues you would like to cover? I don't see any. You can write also in chat. So I will start my introduction with the circ, and we can import circ by calling import circ. And there are few naming conventions you can actually use in circ, which is yeah, for qubit, naming conventions for qubit, which are named qubit and also a line qubit. A named qubit, as you can probably think of, can add a name to your qubit, which may help you tracking which qubits are maybe ancilla qubits or target qubits, or the qubit that you're going to use for quantum amplitude estimation, for example. But in this workshop, we're not going to use this very often. We are more interested in this line qubit. And this line qubit creates a qubit with the index 4. Note that instead of like Qiskit convention, this one line qubit creates only one qubit with the index 4, not an array of qubits. In order to create an array of qubits, we will use the range method. So this one will create a list of qubits with four qubits, right? And they're also indexed from 0 to 1. We can create a circuit by calling circuit, and we also have basic logic gates like X, Z, H, CX, C0, swap, and double controlled NOT gates. But this time, instead of small letters like in Qiskit, we have capital letters. And there are two ways to append a gate. One is to call an append, then gate we would like to use, and then the qubit on which we would like to call this gate to. And so I think that X, Z, and HI and H gate, Hadamard gate are quite self-explanatory. But the CNOT gates, the first argument is the controlled gate, and controlled meaning the target qubit, and the second one is actually the oh no, it's different. Sorry. So yeah. Sorry, once again, the first qubit is the control qubit, and the second one is the target qubit. And we can later then print the circuit by just calling print circuit, and we can see that the first one, this at symbol, is being the controlling and X being the target. And likewise in control Z, we don't have actually, like, because of the phase kickback, we don't distinguish between target and controlling. They're basically the same. Yeah, so we also have notation for swap gate and multi-controlled NOT gate. So the first task is to create a quantum circuit with 10 qubits, and then apply Hadamard gate to qubit 0 and 9 CNOT gates where qubit 0 is the control and if qubit is the target. Is there any advantage of using circ over, I'm reading out the question from chat. Any advantage of using circ over Qiskit? No, they're just, I don't think so there's any advantage. They're just both different programming language. I guess that Qiskit is more widely used, like if you would like to run your algorithm on IBM's quantum computer, and circ maybe if you would like to use Google's quantum computer. But basically both languages can be used, and actually both languages have to be then transpiled to quantum computer, right? Because we are learning about X and the Z gates, but actually they're also natively on a quantum computer decomposed to other gates, and each provider of quantum computer used their own compilation code and different actually gates and implementation for the same circuit. Yeah, other question from chat: are their native gates different from IBM and Google? Probably yes, but I'm not sure about that, to be honest. It depends also probably on the architecture. So if there is a superconducting quantum computer or ion based or atom based, the gates are implemented somehow different, and then maybe some are more efficient than others. But basically, what we like use as basic gates are actually decomposed further into other gates and based on some transpilation circuit that may be actually different. Yeah, so there are also like different levels of abstractions with Qiskit and circ. So they may provide different different functions for and pre-built circuits. Is there access to Google Quantum Computer? No, I don't think so. Maybe it's maybe there is from AWS Web Services where you can access different quantum computers, not only IBM but also let's say IQM for sure and Rigetti, but I'm not sure about Google Quantum Computer, to be honest. So tell me, would you like to maybe quick survey do the task together, or would you like to solve it on your own? I will yeah, you can react to the chat if you would like to do together or on your own pace the task. I will like wait. Okay.
Maybe we could like do a few minutes to that on my own on our web, and later you could show us how it should be.
Yes, sure, no problem, absolutely. So maybe 3 minutes, is that okay? It's not a very difficult task, so I hope that should be okay. Also, let me know if you have any issues with logging to the platform, if something is not working for you. Have you finished? Are you have you managed, or should we wait some more time? Mm, uh, there's a question from chat also. I think that how to change the setting from light mode to dark mode. You can go to settings, theme, and choose the dark mode. But I will use the light mode because some graphics are better rendered, are designed for the light mode, and therefore it might not be that compatible. Okay, yeah, ready. I see. Okay, so let's start, and we can do this maybe for different. I will just copy paste the code, and you also have the solutions here. But yeah, first we initialize with qubit range, then initialize the circuit with a circuit method. Then we append the Hadamard gate to the first qubit. And as you know, in Python, the first qubit is indexed as 0. And then for E in range 110, we append a CNOT gate to first qubit being the controlled, the controlling qubit, and the second being the target. And let's see how this works. Yeah, so this is exactly the circuit we were going to implement. Yeah, more about gates. So there are actually also two different ways to write gates. The first one is as we discussed earlier with append, and then we can write the Hadamard gate and a specific command on each. So this will apply Hadamard gate to every qubit on a list. And this magic star is just doing something magical, which is taking the list and like returning every value of that list. So if you can see some expression here, yeah, but I can probably do this, right? So this is actually not very helpful because this is also a list. But if I first print the star, then you can see that actually this returns elements of that list, and then I pack it again in list. But here this goes as an argument of this on each command. Yeah. There's a question in chat for people like us studying quantum computing. Would you suggest we work on Cirq on Qiskit? I think Qiskit because it's simpler, but Qiskit is like you have pre-built functions that are somehow like black boxes, but Cirq is probably faster and also gives you much deeper control over what you're actually trying to build. So maybe this is more for experienced researchers. But yeah, for the purpose of the QNickel course, we are learning both Qiskit and QNickel, so you have broader range of tools. So yeah, these notebooks were actually designed by the course administrators to be used. So yeah, before we learned Qiskit, and now we're going to learn Cirq, and that's why we're going through these notebooks. But as you will see, I would say it's quite similar to Qiskit. It's just like different naming conventions, and gates are literally the same. It's just the syntax, right? So the same was with other programming languages, right? Like Python and C++. Sometimes the difference is not that much, but basically the syntax. So this is one way of creating a gate. The other is that we can append the gate, like append the gate, but don't. Yeah, but once again, so we can specify the list of qubits being controlled first, and then assign it to a multi-controlled Hadamard gate. And the second method is to assign a z dot controlled on the third qubit, and then execute this method by giving which qubits we would like to give as the controlling qubits. So in the first method, we just firstly specify the target qubit, which is the second. So 0, 1, 2. We have the Hadamard gate here, and controlled by a list of qubits. And the second method is to create a Z gate controlled by the with the third qubit as controlled, right? So here, and the controlled Z's as controlling qubits. So 0, 4 would actually be 0, 1, and 0, 1, and 2, and 3. But since 3 is the controlled, it just skips. Yeah. Another very interesting feature of CERT is that we can have a arithmetic operations of gates. So there's a special gate which is called square root of x, which is simply if this gate is applied twice, then we will have standard NOT gate. But if it's applied only once, then we have like sort of a square root of x gate. But we won't use this gate very often. So it's just for let's say curiosity. Yeah. So this gate will actually, so those two gates combined will actually be a single x gate and NOT gate. So yeah, next we have a task 2, create a quantum circuit with 10 qubits, applied Hadamard gates all to all qubits, and NOT gate from 0 to 9, and Hadamard gates to all qubits. So this is basically the same question as before, but now you can use this on each command, and also this controlled by, because this is with 0 controlled by 1 to 9 qubits. So 0 is the target qubit. Yeah, I'll give you like 2 minutes probably. Write in chat also if you're ready, and then we can start go next. And also let me know if you have any questions in the meantime. Are you ready? Do you need more time? You can write in chat or just unmute yourself. Okay, so maybe, yeah, are you ready, or can you give me some feedback? Yeah, sure. Okay, thank you. So yeah, the solution, I can post it right here. Remember also that you have solutions here if you would like to revisit them. So yeah, once again, we have append Hadamard on each gate, and then append a X gate with to the first qubit controlled by all of the rest qubits. And then once again, append Hadamard to each of them. This will be very helpful. This code snippet will be very helpful for our implementation of Grover diffusion operator, which we'll talk about later today. So yeah, how to run a circuit. In order to run a circuit, we can append a measurement, and to the measure function, we append which qubits we would like to measure, and we can also specify a key. Therefore, if we have two different qubits or line of qubits I would like to measure and compare their results, we can specify different keys and then access those results using those different keys. So here you can specify and execute the program, your quantum circuit, with circuit.simulator, and then run the simulation with some number of repetitions and obtain the samples, and then create the histogram of the results. And as you can see here, it's very strange. Oh. Because we have two with measurement measured 527 times and zero measured 473 times. This is a lot of, let's say, kind of different with the Qiskit, where you have like 0, and 0 ones. But now here we have the binary representation, let's say decimal representation, the binary string 0, 1. And we can convert this to binary string using this function. And as you can see, now you have the provided measurement times. Okay, so there's a question in chat. Are all those quantum frameworks hardware agnostic? I don't think so. They're not really. I mean, every hardware provider has to probably do their own implementation of the programming language and let's say transpilation on their own. Moreover, there are like many different quantum programming language. There's also like language from classic, and they're all using their own transpilation and code, and they're mostly using functional based programming. There's also language provided by Penelane, and this is mostly using for quantum machine learning. So there are very different programming language, even if programming frameworks, let's say libraries, even for quantum computing. And each of the libraries, each hardware provider has to create their own implementation of and transpilation of the circuit provided by the language. So yeah, going back to the discussion with those bit strings, we can access the measurement by calling the key result that we specified earlier, and we can print the results individually. So here we have like those 1000 rows step by step, provided the list of what result was called when. Yeah, we can. So before we had the measurement of all. Yeah.
Like earlier, what was this 2 and 0? I didn't get it. Like, why we see in this counter, like why we see 500 of 2 and 473 of 0? Like, how should I understand?
Yes. So these are the measurement results.
Yes. Yeah. So what are these 2 and like what we created that the output of the measurement is counter 500 times and 0 less than.
Yes. So maybe we can print our circuit.
Yeah.
So it is better, visually like better. So no, this is actually. Well, yeah, it's range with 2. But QList is, yeah, it's 2. Yes, okay. So with this Hadamard gate on the first qubit, we have states that are 1, 0. Let's say maybe it's a superposition of 0 plus 1 on the first qubit, right? And the 0 on the second qubit, right? Which is equivalent of calling, let's say, 0, 0 plus 0, 1, right? Of course, some constants, and but yeah, we can omit those. So the measurement should output as those 2 bit strings. It also depends on the convention on whether you first write 0 and 1. And as I can imagine here, this should be rather reversed. So it should be 0. No, this was good. Sorry. It should be 1, 0. Yeah. So this function, samples histogram, returns the decimal representation of the string, right? So when we convert from binary to decimal, the 0, 0 is 0, and the 1, 0 is 2, right? So this shows us that
easier from, like, if I want to think about it as the eigenstates of the superpositions, then it's like 0, 1, 2, 3 up to 2 to the power n.
Yes.
Okay, I see.
Yes, this
thanks.
is, yeah. So in Qiskit, maybe it was easier because we had only qubits in 0 and 1s. But let's say for advanced users, and if you're trying to like do some arithmetics on quantum computer, then like this bit string doesn't tell you anything, right? It's more convenient to use decimal sometimes. So that's why like Circ already provides us the decimal representation automatically. So we can say that actually 1, 0 was measured 500 times, and 0, 0 was measured 400 times. But actually, in the decimal representation of those 2 bit strings, it is represented as 2 and 0. Yeah, have I answered your question? I hope so.
Great.
Sure.
Great. Thanks.
Yeah, so going back to measuring only 1 qubit, we can just specify the 1 qubit to measure, and we can all, let's say, do the same, and we obtain very similar results with 50-50 probability. Yeah, so now task 3 for you. Implement a circuit from task 1 and measure all the qubits and simulate your circuit for 1,000 times. So you can probably copy paste your codes and then just copy paste those results. Maybe I will give you like 1 minute, but since we already have most of the work already done, we can just copy paste our code and see what happens. I will just also remove this print here and do it here. After the measurement, oh yeah, also we have to measure it. So maybe he will be more easier for us to do this. Yeah. Measurement. Yeah, so we have task 1, measurement, printing circuit, and let's see what happens. Yeah, so basically what we can conclude from it is that that yeah, this Hadamard gate creates two different superpositions, but then because this is in superposition of both states, and this controlling gates are transferring all the subsequent bits, the result is zero. Either all are zeros or all are ones. So yeah, now debugging the circuit and let's say circuit representation. So before, with only the measurement, we had a simulation when after the measurement, the quantum state, let's say, collapses to either 0 or 1. And we can only, like, when we measure, we can only see a bit string. But if you don't provide a measurement and you just simulate the circuit, then you are able to retrieve the state vector. So in circ, the state vector will show you the superposition of the output, let's say, vector, right? And here we have 2 qubits. Maybe we can also print this. Yeah, only Hadamard gate, even though we initialized with 2 qubits, but we didn't specify any gate on the second qubit. That's why in the output we'd see only 1 vector. But if we specify the identity, so do nothing to qubit 1, the circ automatically captures that and also simulates or returns the state of the second vector. And we can also print the circuit. Yeah, so we can see that doing nothing to the second qubit results in just state 0. And we can continue and measure all the qubits. And if they're measured, then we only have a one, we can observe only one state, right? So after the measurement, we don't have a state vector, but rather just a vector. Yeah. And we can also do this with more qubits, like range 4, and applying Hadamard gates on each qubit. It's very similar. Yeah. So in task 4, you have to create a quantum circuit with 4 qubits, apply a Hadamard gate to each qubit, control Z gate to qubit 0 and 1, use the simulator without measuring the circuit, and check the entries with negative sign. So this is, yeah, basically the phase kickback, I think. So yeah, maybe I'll also give you 2 minutes for this one, and we will be almost finished with implementing circ, the circ notebook. Okay, so going step by step through the solution. First, we would like to create a qubits with a circuit, a list with 4 qubits, right? Then we initialize the circuit with circuit. Then we have apply Hadamard gate to each qubit, which is simply append Hadamard on each of Q list. Then we have a controlled Z gate, with the first being as target and the second one being control, but actually for the control NOT gate, it doesn't really matter.
Maybe two
And,
parentheses are missed in apply H.
Once again?
When you apply H, yeah. Okay.
Thanks. Yeah.
One more, maybe.
Yeah, you're right. Thank you. And finally, the simulator. And let's see the result. So the first one, we have the output vector of the first and the second qubit. Maybe also it's better to print the circuit to see what we are working with. Yeah, so based on that, we should see that those two are somehow interconnected. So we have the superposition of 4 different states. And here we also can see the minus sign of the 1-1 phase. And this will be very important for the Grover implementation, where we also would like to flip the sign of our search key, but we will cover that in a second. Yeah, and later we have also Hadamard gate to the second qubit, which is the state vector we already know, and likewise on the third qubit. We can also create a matrix representation and print the corresponding matrix, unitary matrix of a gate. And for the CNOT gate, you should be already familiar with the matrix. So we have first two elements are ones on the diagonals, and then we have to flip or apply a NOT gate on the second two states. Yeah, I assume that you're familiar with those matrix representations. If not, you can write in chat and I will try to explain you how those matrix representations of gates work, and likewise how to multiply the states. Yeah, is it familiar for you or not really? Yeah, I guess so. Okay. So we have a matrix representation of CNOT gate, and also the square root of x gate is simply this one. So it's it's just, let's say 0, 5, both on real and imaginary units. Those imaginary units, yeah, they are there, but
so like maybe it's just a typo, but is it C root x? Like, is there any reason that in the print you put C root x in the second line?
Yes,
Or
I mean
it's
it's
just a typo?
yeah, it's
yes,
okay. Yes.
I thought
absolutely right. Thank you. And yeah, we also have the representation of the Hadamard gate, but on 2 different qubits. And right now, previously, the Hadamard gate, let's say, on 1 qubit is just 1/square root of 2. But let's say this is 1/square root of 2, and here with the minus. But on a 2x2 Hadamard gate applied on a 2 qubits, this is just 1/2, and we also have some minus signs here and somewhere here and there. Yeah, we could also do this like algebraically and apply the tensor multiplication. Let's say I don't know if you're familiar with it or not really. Yeah, we will also not really use this this multiplication, but but this is somehow how you can visualize the matrix representation in Circ, and we will actually use it. Okay, do you have any questions to this first part of Circ? I believe that like learning a new framework is just is more, let's say, valuable if you already applied to like real world problems, and therefore we'll, I think, go now to the theory of Grover algorithm, and then just simply apply the knowledge of this notebook to solve problems from from Circ. Yeah, I don't see any questions, so I will move to now implementation of Grover algorithm. So yeah, I will have prepared the notebook here, and I will start. Maybe Rice, give a reaction whether you already have already familiar with Grover algorithm or not. If you are, then raise your hand, or but I will also see if thumbs up. Yeah, I can see two thumbs ups. So 4 maybe. So most of you, I assume, are not familiar with the Grover algorithm. So yeah, I will try to give you a very intuitive introduction to this algorithm. So yeah, so Grover is designed for search. And if you have a list, let's say a database with some numbers like 1, 2, 3, 4, 5, 6, let's say, and more. And you would like to find a secret value, which is your key. And you're looking for this key. And the question is, how many steps you would need to make classically to find this key. So let's imagine a black box function, which is a machine which outputs you true if this number you input is the key, and false if it's not. So maybe you can write in chat, or let's say classically, you would have to check, in the worst case, every single number to find those key, right? If you would like to check, let's say, 1 by 1, and the key is, let's say, in the list of 100, this is our key. So if you were going step by step, oh, something happened. I don't know what. Hard to. Okay, sorry for that. You would have to make 1,100 queries to this function, f of x, let's say, to determine whether you have found your key, your number with your key. But yeah, in quantum computing, we expect to do it faster. And the question for you is, how much faster do you expect it to be? So I will write how many queries you would need for this in chat, and you can vote for your answer, and then we will discuss it. So let's say there is 1 query. There is square root of x queries, log of n, square root of n. I don't know if I can edit, yeah, square root of n. Yeah, I assume square root of n, yeah. And let's say log of n. I see that some are already knowing what the answer is. And yeah, the correct answer is square root of n. And maybe raise your hand if you know why this is square root of n. Because I know that some people have some intuition, but do you actually know where does the square root of come from? Not really. I don't see any hands. So I assume that, yeah, today we will go once again step by step through Grover algorithm, because it's crucial to understand to understand it for max-cut problem. So yeah, in quantum computing, with Grover algorithm, we will have just square root of n queries at worst, in the worst case scenario. So Grover algorithm is actually composed of two different steps. First step is the mean reversion. And the second step will be the phase flip. And we will first try to build an intuition of those two steps. So imagine that you have a histogram of all possible queries. So we have 0, 0, 0. Let's make it 8 for simplicity right now. 0, 0, 1, 0, 1, 0, 1, 0, 0, up to 1, 1, 1. And imagine we place it in a superposition of all those states. So therefore, we can write that probability of measurement is just some number. This is, if it's superposition, then this should be 1 over square root of n. This is not how this, it's very tempting to see why this is so, but we'll see why the n's not connected here. And we would like to construct an algorithm that actually gives us at the end our correct answer. Let's say 1, 1, 1, which is our key we're looking for. The highest probability, almost 1, and the others are almost 0. So we would like to construct such an algorithm. And very interesting property of this is that we can, doing this mean reversion and phase flip, actually go from this state to that state. And this works as follows. So if we try to now implement the first phase flip with an oracle, a very special oracle, that it applies, let's say, a unitary gate, or unitary gate u on some value x. This will return the minus value of that state with the phase flip, as you learned on Monday. And also, this is provided that our oracle state omega is equal to x. So omega is actually our secret key that we're searching for. And if it's not, then we'll just leave the state unchanged. So with this histogram representation, you will now have a histogram with all the values unchanged, except for the last value, which will have a negative sign. Maybe it shouldn't be probability, but should rather be amplitude. And once again, I have the issue with my pen. Oh, no. I'm sorry, this is not supposed to happen. I assume this is because of also recording issues. Yeah, so go back. Sorry for that. This should rather be an amplitude of our phase. our mean quantum state. And by doing so, we have different amplitude states. And now we have different step, which is the mean reversion about the mean. So what does it do? So here, if all the states are in the same state, let's say, we can say that the mean value of all those states is somewhere here, right? This is a single value. But now the mean is slightly lower. The mean, because this is a negative value, the mean will be somewhere here, right? So we would like to now create an algorithm that reverts the amplitude about the mean. So this one, after the transformation, should actually be in the same distance as this, as to the mean, but below. And likewise, this should be in the same distance as the mean, but above. So after the transformation, we will have a histogram looking like this with the, let's say, previous mean. So now the bars are lower with the values that are not our key, and higher for value that is actually our key we are looking for. And this is great because we are searching for key. And by repeating this algorithm a few times, we are able to actually go back and diminish the values of unwanted states and increase the amplitude of our key, our searching value. And we will discuss how to construct both the mean reversion and phase flip gates from scratch. To do so, there's a very convenient way of drawing a quantum state, which is simply on a unit circle. And we can create a represent the state of our key as a vector. And this vector will be the vector of our key. And this will be the vector perpendicular to our key. Let's say this one. Later you will see how this is implemented. So in our case, when we know that we are looking for this 111, the vector will be zeros and then 1 at the end. And note that sometimes it's very confusing because in the original statement of the problem, we don't know what number is the key. But in order to understand it better, we assume that we know the key and then construct an algorithm based on that. So sometimes it's confusing where it's actually known and when it's not. But for now, we assume that we know the key. And for the purpose of, yes, learning and constructing an oracle, we assume that we know the key and we're constructing a circuit to actually find it. So that's why it's sometimes an ambiguity of what is actually, what are you trying to find, since you already know it. But yeah, I'll leave this for now. So we are searching for the key, and this is the vector representation of our key. And likewise, this will be the uniform superposition n-1 of all the states except the key. So with our initial setup, we have all the states in the superposition of equal amplitudes. And on this graph, this would be equivalent of a vector somehow like this. This is, we'll call our balance state B. This is just superposition 1 over square root of n of all the possible numbers. And this as a vector representation. I don't know if you're familiar with this vector representation going from the bracket notation, but this should be also equivalent to, let's say, 1 over square root of n, 0, 0, 0, 0, plus 0, 0, 1, plus, and so on, to 1, 1, 1. Right? Okay, so with that being said, we can first implement a reversion, a phase flip. So our state is we're looking for is getting a minus sign. So what does it mean? This means that the component of our key is getting a minus sign, but all the components with where there's no key stay the same. So this is actually equivalent of flipping the state vector around the x-axis, which is the vector perpendicular to our key, vector that does not contain our key. So this is the first step. Second step, reversion about the mean. And since our mean is just the b vector, we can flip it. Let's say, this is the first step. And the second step will be this. So, yeah, okay. Maybe I'll also, it's okay. Yeah. So there's some angle theta here and another angle theta here. But now we have successfully, with those two steps, rotated our state vector, which we'll call, let's say, v, with the angle of 2 theta. And the question is, what is this theta now?
Sorry, Krzysztof, this 2 theta? 2 theta is from okay,
this
okay, got
to
it.
this.
But
right?
This second step is not the same as what you explained earlier, right? Because you are you assume that the state that we started with, like we make the mirror with respect to that. So so previously when you were saying that now the mean is a slightly lower because the last eigen value, let's say, or the state we flipped, that's not. So yeah, this is what you explained here. It's not the correct.
Yes, that's right. That's right. But actually, the mean is slightly lower. Yeah, I see your confusion here right now. Maybe it was not that good explanation after all. But
and that 2 theta should be 3 theta, right? Or I'm mistaken? This angle that you pointed as 2 theta, it should be 3 theta.
No, this is actually correct. But
because
why is that?
You make the like, I think it should be 2 theta, because like from with respect to which vector you make the mirror.
With this, I make the mirror with respect to.
So which means from there you should have 2 theta.
Let's say this vector here, right?
Yeah. So already this vector with like the angle between this vector and the lowest one.
That is correct. Yeah, thank you. Thank you for that. Yes. I will try to like erase this now. Yeah, that's yeah. Thank you. Oh no, actually once again this error with the pen. Really annoying.
Maybe you need to give it some time for the recording.
Yeah, because I have like additional buttons with this recording, and sometimes it's when I hover over them, they're confusing. But yeah. So once again, yeah, thank you for that note. So once again, we have a new vector with the reversion about the mean. Which is now, yeah, 2 theta from this one. Yeah. So what is this theta? So this can be said as, so let's say maybe this angle, let's say alpha, is the same as cosine, maybe in other words, this line segment here is the cosine of alpha. And as you probably know from linear algebra, or maybe you don't, we can calculate this cosine from the dot product. So this will be the dot product of our v vector projected onto the key. And we can write this as, are you familiar with, maybe raise your hand if you're not familiar with this Brown notation. What does it mean? Yeah, I think all of you are familiar, and you can proceed. So yeah. So this v vector will be almost something like, let's say maybe, well, the b vector is, sorry, yeah, this should be b, is ones, and right now the key is everywhere 0 except the last one. So the result is actually d, and it should be 1 over square root of n here. So just 1 over square root of n, right? So this is it. On the other hand, this line segment here will be the sine of theta. And since
that's
this is
sine
also
of alpha, right?
Sine of alpha, right? Yeah. No, so this is sine of theta. No, this is sine of theta. So yeah, this should be cosine of theta also. Yeah, sorry, this is cosine of theta, of course.
No, so sine is the like the front to the.
Well, once again,
Like because the sine, like when the argument of sine is small, the sine x is x.
yes, that's right. That's
So
what I'm going for.
then it means that this front one is the sine of theta or cosine of alpha. No, that's not right.
What?
The front,
Once again.
yeah.
Yeah,
This should be sine of theta or cosine of alpha.
No, because this is with the key here.
Yeah, but then you can write it alpha if you want to write it as cosine, because sine of alpha is equal to cosine of theta, and vice versa.
This is projected onto, yeah, this, yeah, sine of, oh, let's say, sine of alpha. Yes, this is correct. But this is
which is like cosine of alpha is equals to sine of theta, if you want.
so alpha equals the sine of
Yes, yeah,
90 degrees. Alpha plus theta is 90 by 4.
yes.
so sine of alpha equals
That's
to
a-
cosine.
Yeah, wait a second. This for sure, this should be theta.
Yeah, which is the front one, which is exactly what you wrote, which is like the theta goes as 1 over square root of n, right?
Yes.
So
Yes,
sine
that's
of
right.
theta is equal to cosine of alpha that you calculated up there.
Yeah, that's right. Now I'm back. But I wanted to this is cosine of alpha. Yes. But the other approach is that cosine of theta will be the dot product between those two. But this is more complicated, right? Yeah. Thank you for that. I was lost at some time. Yeah. So right. Cosine of alpha equals sine of theta, which in a Taylor approximation in the first order is just equal to theta, and that's why from this we can say that theta is equal 1 over square root of n. And as you can see here, by applying those two steps, so phase flip and reversion about the mean, we have two steps of theta, right? So the question is, how many steps do we need to get from here to our key? And the answer is, it's pi over 2 divided by 2 times theta, right? Because we need one step of the algorithm, which is mean reversion and phase flip, transfers us as if it was rotation of 2 theta. So we need 2 theta times, let's say, n times, right? So this n is not good. Let's say, number of iterations, let's say. So 2 theta times number of iterations should approximately give us pi over 2, right? So expanding this gives us pi over 4 time divided by 1 over theta, but we know that this is actually square root of n, right? From this one. This is why Grover algorithm has a quadratic speedup, which is also denoted as a big O of square root of n. Yeah. Do you guys understand this more or less? Give your thumbs up or raise your hand, please. Yeah, I see 1 hand, 2 hands, 3 hands, 4 hands. Okay, yeah, you definitely will have to once again revise this algorithm. There's also a dedicated course, which is QBronze, and you can find and search those materials there if you're lost with this Grover's algorithm implementation. I can maybe briefly show you. So if you go here and QBronze, you should find the keyword QBronze. Yes, you should find the materials explaining basics of Grover's algorithm. Quantum of Qiskit, I think it's here. Grover's search one qubit representation. And we will also, very important question is, what if what if there are more keys, right? So what if there's not only one key, but actually multiple keys? Well, the answer to that question is that we will have more, instead of this one, we will have more ones. So zeros, ones, zeros, zeros, ones. But also our states will change. So from this one to maybe k keys. Yes, we will have like k numbers right here. And also our state vector will change from this one to square root of k over n. And therefore, if we do the math once again, so for k keys, let's say k number of keys, we, let's say, substitute the result here to be k square root of k over n, and then once again work out this theta, which will be then equal, this number of iterations will be equal to pi over 4 square root of n over k. And please remember this formula because it will be on the assignment definitely. So yeah, and then now the question is how to implement all of those gates, because yeah, I've been showing you here those vectors, how to map from one another, but we don't know how to implement it actually on a quantum computer. So let's start maybe with the phase flip. So we know that in a state of all the superpositions, let's say 0, 0, plus 1, plus 0, 1, plus 1, 0, plus 1, 1. If this is our key, then we would like to construct an oracle that would change this value to minus 1, 1. And as maybe we saw earlier, this can be actually done with the controlled Z gate. Yeah, here is what I was talking about, right? We had the controlled Z gate, and this changed our state of the 1, 1 qubit with this minus phase. So yeah, so we saw that, for example, to this two-state qubit, it is sufficient to call a control Z gate. And in matrix form representation, this will be equivalent to 1, 1, 1, and minus 1. And likewise, and this is all, there are all zeros. So yeah, if our oracle, yeah, this will be our oracle. So if our search key is minus 1, 1, 1, we should give a minus 1 to the matrix form representation corresponding to that oracle, to that key. And maybe right now, for simplicity, I will write zeros here everywhere. I will later remove them. No, there are too few of them. 0, 0, 0, 0, 0, 3, 2, and 1. And these correspond like to states 0, 0, 0, 1, 1, 0, 1, 1, and likewise here 0, 0, 0, 1, 1, 0, and 1, 1. So by this matrix transformation, you can see which vectors from, let's say, this column are transferred to what vectors here. So as you can see, these vectors stay unchanged. but the last vector is changed with the flip -1. And for example, if we were to search for a oracle, like search for keys with 0, 1, 0, 1, yeah, this one, plus, maybe it's too long, sorry, plus 1, 1, we would construct a matrix which form is 1 for state 0, 0, 1 for state 0, 1, -1 for state 1, 0, and -1 for state 1, 1. Yep. So this is how this should work. On the other hand, if we had an oracle like 1, 0, 1 and 1, 1, 1, this would be an 8 by 8 matrix, which is kind of tricky, but we'll do a different trick. So we will tell that this is a vector 1 plus superposition of 0 plus 1 and also a 1. Yeah, do you agree with me? I think so, you should. There's maybe also this 1 over square root of 2 here, but nevertheless. So with this one, we can construct this state. Let's say it will be then, let's say, huge oracle with some zeros here and 2 ones. Sorry. With ones on diagonals and some with -1s corresponding to those states. It's like a representation. It's not very technical, but we can do this by applying a single controlled NOT gate to the first control Z. No, sorry, not control, not gate, just controlled Z gate to the first, yeah, so indexed 0 to the first and third qubit indexed 1. Yeah. Why? Because if we have 0, I mean, if this one is 1, then we should also change the phase of the last qubit, and basically this should be untouched because they're in a superposition, so it doesn't matter. Maybe it's not plus here, but it's actually a multiplication, tensorized multiplication. So yeah, so to construct the state, you should only use one CNOT gate with 0 and 1 as controlled qubit. This may be more clear if you consider all of the superposition of different gates, but again, this is not important. So to construct an oracle with the keys we want to search, we just, let's say, put minus sign in front of the ones that are actually we're interested in, which state we're interested. So yeah, that was the phase flip. Operator. And now we're going to solve for the reversion. Reversion about the mean. Reversion about the mean operator. And if you, let's say, try to do this first classically, then from a scalar perspective, we can say that the x nu should be equal to x old plus let's say 2 minus mu, or let's say, no, it should be x, yeah, x old minus mu. I think so. Not. Something's wrong here. Yeah, this should be 2 times mu minus x old. Yeah. Why is that? So if we have, let's say, our bar that is positioned here, and we have some mean value, then the height of this should be reduced to the later bar, right? This should be our value. But this is actually the value of, this is a value of x old. This is our value of mu. And we need to subtract from the value of x old 2 times the value of the difference, which is x old minus mu. Right? So we have this difference, and we have to subtract it 2 times, or let's say add it to the old. To the old. Yeah. Actually, yeah, this is the same as x old minus 2 times x old minus mu, right? So we should subtract this 2 times. But expanding this further gives us 2 mu minus x old. Let's maybe start from this one here. 2 mu minus 2 times x old minus x plus x old, which is just 2 mu minus x old, right? So we have the value for our x new and based on our old state. And actually, we can also, let's say, have a vector analogy. So from a vector perspective, this x new will be, let's say, an operator 2a, which is now an operator, minus I, which is an identity operator, which is I applied to, let's say, x old is just x old, does nothing. So this matrix should be applied to x, x old, to obtain x new. So yeah, this is like classical way of subtracting the mean, but now we have to create, let's say, a quantum analogy, a linear algebra analogy, and this is the operator we would like to construct, and how to deconstruct it further into quantum logic gates. So it seems is like proven that this new operator, which we call US, is just 2 times, and then this will be like our this B vector minus identity operator. And how to decompose it further? We will take this, we will then examine what is like what is the effect of some no, we first have to do something else more to be able to reconstruct it. So yeah, bear in mind with me. So this is just 2 and Hadamard gate applied to state 0. Right? This B vector was a superposition of all the states. So this is a Hadamard gate applied n times to all those qubits. And we will, this is maybe not, I will do something like this. So this is actually, in terms of quantum circuit, this is just applying Hadamard gate to every single qubit. This is mathematical notation of this. Yeah. So this creates our vector of equal superposition B. And likewise, we also have, from this side now, superposition of all the states with the Hadamard gates applied. Right. And also minus this identity. I will also write it as this unitary matrix. And this is just one on all of the diagonals. So we can now take this further and decompose it, say, into the brackets. So this one we can also write as applying Hadamard gate twice. So this is the same as twice the Hadamard gates. So our equation now becomes 2 times Hadamard gates applied on every qubit times on the 0 of qubits. And yeah, again, Hadamard gates minus Hadamard and again Hadamard. And we would like to now decompose it into 2 different set of gates. And now this thing will become Hadamard. We'll take those both Hadamards, let's say, in front of the bracket. So this one and this one, and likewise this one and this one. So this one is just this 2, and then 0 minus 1, and this is just a scalar now, let's say, or maybe also be the identity matrix. And again, Hadamard applied to both sides. So we will now examine what is the effect of applying, let's say, this gate onto our state X. What happens to it? So we will consider 2 cases. If X is 0, and if X, maybe let's say in this sense, if 2 cases, if X is 0, then we have that we have operator like 2, 0, 0, minus 1 applied to state 0, which is just expanding the bracket to 0, this one 0 minus 0. And this should, yeah, give me just state. This should give me state. Okay, this is 1. So this is 2 times 0 minus 0, which is equal to 0. And now we will consider a case where where x is different than 0. So if x is different than 0, we have, let's say, equivalence of applying this to -1 on x, and this should be equal to 0 x, and here's x, minus x. And this, because x is different than 0, this is 0, because they're like perpendicular to each other. So therefore, we have obtained minus x. But we can also write, what does it tell us? This tells us that the 0 is untouched, and the x has a negative sign. Does that give us something interesting? Well, so in this mean reversion, what we are actually trying to achieve. I get lost a little bit. It's also like sometimes very confusing, but once we go to the notebooks, I think it will be more clear. So okay, so maybe from the beginning, once again, this operation should be sorry, I lost my notes. No, it's not there. Oh, sorry. Just a second. Let's express this as let's say -d, or some notebooks. They're also, the notes are also in the notebooks, but yeah. So you have -d, and since no, I'm not able to reconstruct this argument right now. I'm sorry again. So once again, we have a state like this, and we would like to create gates that face the flip the face of our x, and actually we can also do that by decomposing the gates further into, let's say, x and Control Z gate. So before we have those Hadamard gates, and now this, let's say, call it, I don't know, P, let's say, we will further decompose it into X gate and Control Z gate. So right now, this circuit will look like Hadamard gates applied to each of the qubits. Then we will have X gates. And at the end, we will have controlled Z gate. And once again, Hadamard gates, which are coming from that one, right? So this will be our Grover diffusion operator, which is, yeah, there's also this mean reverting operator. Yeah, so we have two sets, and one is this mean reversion, and the other is the phase flip. which is just can be implemented with the single or some multiple controlled NOT gates, controlled Z gates, sorry. Okay. Do you have any questions for now? Maybe if we will go to notebooks, then will be more clear why we do this exact setup right here. Okay, so let's go to Grover. I think this is it. Yeah, so the Grover algorithm looks as follows. We have, this maybe circuit implementation is more clear right now. We initialize the circuit with a superposition using the Hadamard gates. Then we apply an oracle. And the oracle is the phase flip that actually flips the phase of our key. Then we have this Grover diffusion operator, which is the reversion about the mean. And again, we repeat this step by steps. And once again, for there are k different keys, we apply this square root of n over k times. And so on. So task 1 is to create a 4-qubit circuit with initialized Hadamard gate on each circuit. And we should convince ourselves by displaying it. Bring the quantum state of similarity without measurement. So yeah, we're going to implement this Grover algorithm. Maybe I will give you 2 minutes. And in the meantime, I will write my own solution. If you don't want to, you cannot, you don't have to watch it, just implement it. But yeah, I'll start writing. So I don't know if you're ready or not. Yeah, he's ready. So we initialize the circuit with circuit, apply 2 use 4 qubits, apply Hadamard gate on each qubit, and then print the circuit. Again, here is the printed circuit, and we have, as we confirmed, the superposition of all the possible states with 1 over 8, so 2 to the 3 different states. Yeah, so now we're going to implement the simple oracle, and as I said before, we would like to mark the state 1111, and we can do this by applying a multiple controlled CNOT gate. And there's an explanation here that says this should flip the sign of this 111 state to -111, but leaving the others unchanged. And this simple Z operator will not be enough, because it will change the state of all those states where there's 1 at the end, which is not what we want. We would only flip this state. So we should apply a controlled Z operator that flips the phase only if all the first 3 qubits are 1. Maybe here you can also view it a little better if I do this. So executing the circuit, we have a controlled Z gate with first 3 being the controlling and the last one being the controlled, but actually it doesn't matter. And yeah, in general, we can create an oracle with multi-controlled gates. And here's also, once again, let's say a little bit from Circ code itself to different implementations of creating the controlled X and controlled Z gates with different qubits. So we have, again, two gates with the third qubit being the controlled one and controlling with all the list, qubits in the list. And also we can do the same by saying, again, in this setup is, let's say, different from the simple controlled NOT gate, because right now the first are controlling and the last one is the controlled one. So the second one will be the controlled qubit, the target one. Yeah, so now we can look for the implementation of this matrix form, as I showed you before. So with this matrix representation, this simple controlled Z0, multiple controlled Z gate, we have a matrix that's, let's say, quite ugly printed, but you can see that on the diagonals here we have ones, and only the last one is -1. So this confirms that this is our desired circuit. And with this one, we have slightly different approach because we have two controlled Z gates, and this changes the representation of our matrix into the form that this state, so this is 0, 0, 0, 1, the free, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1. This is state 0, 1, 1. Maybe let's track it so it's state 0, 1, 1 plus the state 0, 1, 0, 0 and 1, 0, 1. Yeah. And then everything remains unchanged also. Yeah, so you can see the difference of applying a single multiple controlled Z gate of applying two separate single controlled Z gate. The states are different. The matrix representation are also different. Yeah, and this J also stands for the imaginary unit, but we don't need to talk about it yet. So for the Grover diffusion algorithm, we have something like this, which is 1/2 and 1/square root of n on every single matrix. And this is very similar to what I showed you, and maybe you can see right now the resemblance of it. And the diffusion operator is implemented as Hadamard gates and X gates, a single controlled Z gate. And once again, X gate and Hadamard gate. And in general, yeah, we can apply Hadamard gate and NOT gates to each qubit, then use Z gate and do the same. And right now it's, let's say, give us 5 minutes to implement this circuit above using the Grover's algorithm. And maybe I think in your notebooks, I'm not sure, but it may have been something like this. So if you cannot see the image, please just double click, use \/ and you should see the image if you cannot. So yeah, 5 minutes for that.
Kirchhoff,
Yes.
is there any way to like force the circ to present like in the matrix form to force it to present only the real values while we have these
I'm not sure. I will check it. I don't know the exact solution right now. But I don't think so, to be honest, because in general, those matrices are complex valued. So you would lose a lot of information from that, and I don't suspect it is possible. Or maybe I checked, maybe there is a solution to your question. This is, let's see. Let's see what happens this time. It's U matrix. Yeah.
Okay.
So yeah, thank you for that. I mean, it clarifies a lot. So you can just use this one.
Of course, we need to check first that it is like a real value. I mean, the imaginary.
Yes, because it's only like truncates all those zeros, right? So if actually your it displays only the real values. If your matrix is complex value, then it will lose your information. But yeah. Maybe in the meantime, while you're solving the exercise, I can also show you this with yeah, that looks a little nicer. So we have only this -1 here, while here we have in both cases. So yeah, the solution here is just to use on each argument. And next, do this control Z gate. So the target is the second qubit, and the first and the second are controlling ones. Yeah, and I will also do this trick with the U matrix. Yeah. And right now you can see that every single entry is, let's say, -1 over square root of n, 1 over n, let's say, except the diagonal, which is also having this 1, right? So we're adding 1 and then subtracting this matrix all over the place. So this is it. And yeah, now let's go to Grover's algorithm. So your task right now is to combine all of the pieces you had earlier. So the oracle, which is simply, let's say, sorry, oracle, which will take and search for the state 1, 1, 1, 1, and the Grover diffusion operator, which is simply this circuit here. So you can actually try to copy paste the codes, and maybe we'll like do it in the meantime. Just by copy pasting, because it's faster, right? So here we have this multi we would like to get, but this multi is also, I think, for free gates. We'll also need to modify it. Append Z, but this whole time will be free, controlled by, and we can simply delete this by calling QQ. And I think this should be fine. This should also be different, I guess, because right now we have 3 qubits also only. So we can also visualize the circuit. Yeah, we have 3 qubits, as we can see, but now we need 4. So we also need to change this one to 3, and also probably do the control by QQ. And yeah, so because we have like more states, we need to implement this algorithm more times. So that's why we have for E in range 3. But for, like, let's say, try to print it to see if it's good, we'll only 1 was never closed. Okay, why is that? I know why. And now it's something different with Oracle. Yeah, so I think I cannot just on QQ. I need to do on a list specifically.
But maybe you can use Q like as a as an array, like from 0 to 3. Yes.
Yeah. That's exactly what I meant. Yeah. Oh, it's still not the case. Or not, operation not terrible. Append Oracle. I know why. Because we have to somehow change our notation and use a yield command. It's somehow, let's say, different, but it's how functions in Circ work. So if we have a function that we would like to apply on our circuit, we have to use the yield command, and then yield just simply the gate we would like to use and apply on our circuit. So it's not just append right now. Append is for, let's say, gates in, let's say, a row. But now if we would like to define a function and apply this function to our circuit, we drop this append method and add a yield method. And this should now work. And as you can see, we can now use append and the function, which yields all the gates. Yeah, so this is it. So as you can see, we have 4 different steps. The first step is the Hadamard gate, the initialization. Then we have our oracle, and then we have the Grover diffusion operator, which consists of Hadamard gates, X gate, Z gate, and once again X and Hadamard. And as you can see here, very gibberish output, but this is likely because I have created only one iteration, but as you can see already, we have most of the measurements are towards 1, 1, 1, 1. So right now we will go back to 3 as it was before. And yeah, now the measurement count increased drastically. So yeah, we have like a probability of not measuring 111. So actually probably of measuring, yeah, our circuit is 95%. Yeah, and this section here actually is a little bit of a derivation of what I was trying to show you before. So we were implementing this 1 minus 2, and here is, like, say, the reverse explanation. So actually the Grover diffusion operator is 2, this matrix minus 1, and this is equivalent to the, let's say, we can probably do a print screen and show you, I can show you this on the, yeah, here. So this is equivalent to this BXB, right? Because this is also equivalent to 1 over square root of n, 1, 1, 1, 1, 1, and also 1 here, also 1 over square root of n. So if you multiply, this will becomes this matrix here, right? And then from that, there's an argument that the fusion operator can be expressed as D, and where U is those Hadamard's, superposition of the vector of equal superposition. So this is exactly decomposed as Hadamard to the power of n. And if we go back to this, we have explanation that well, the effect of D on a given state psi is we will get the state phi, but we will implement, yes, this D with minus sign because they have identical observation probabilities. So it doesn't really care about this, whether it's which state it is, because after all, we have the same probability of observation. Yeah, this, well, this can also be viewed as just on this graph here, doing something like, let's say, with this minus sign face here. So previously, this should be go like here. And this actually can be viewed as reversion with about the zero state. So the zero state is difficult to say where it is exactly, but it's somewhere, let's say, here. Maybe not exactly. But it's difficult to display graphically. But we would like to do a phase flip about the zero state. And this derivation here actually shows you how to implement this. And here we have, once again, what I was showing you before, that if x is equal to 0, then this whole expression becomes minus 0. And if it's x is different than 0, it becomes x. So how to get this? Well, we can do the same with phase flip. So the phase flip is just the Hadamard gate, the Z gate. But if we first initialize this all with X gates, then we can, and then apply this Z gate, then we will get the reversion about the, let's say, the phase flip of the zero state. And if you get the phase flip of the zero state, well, then we are, let's say, in home, and we can successfully implement this Grover diffusion operator. Yes, just flipping the amplitude of state 0. So how to check if the quantum state is equal to 0 and flip its amplitude? Yeah, we just convert all qubits in state 1, as I said before. So applying X gate to get the one state, apply multi-control Z gate, and then go back to the 0 state by applying the X gate again. So yeah, this is a step-by-step, let's say, implementation of Grover algorithm. If this is not enough for you, then I highly recommend for you to go to the Qiskit QBronze lectures and see Grover search implementation. There are different, it's not rendered correctly in GitLab, but you also get different notebooks, and maybe if not everything here is right clear for you, then you can go back and revise this Grover algorithm, because we will use this Grover a lot during tomorrow and also on Friday to solve the max-cut problem. So once again, the most important things from today's lecture is that from the Grover algorithm, we have 3 steps: initialization, oracle, Grover diffusion, and then repeat this n times. The oracle can be implemented by controlled Z gates, while the Grover diffusion operator can be implemented by those Hadamarts, X, Control Z, X, and Hadamarts. And by applying this circuit over and over again, we will just simply get our search value, our search key in square root of n time. And what you will actually also, from the information you will need for the from today's assignment, is how many qubits we would like to need for number of search elements. So if we would like to search for, let's say there are, 84 elements in our database, we would need 2 to the n qubits, right, where n is number of qubits. Why is that? Well, we can, because if we're searching, for example, for 111, then we can create a superposition of all the states, which are 0, 0, 0, right? 0, 0, 1, and so on. And there is 2 to the n of those possible states that we need. So this is a question you would like to need, and we can also transfer this into that n equals log base 2 of, let's say, hashtag, right? I think so. If I'm not mistaken. Yeah, that should be it. One more question is about how to construct an oracle. So here I showed you how to, let's say you can think of constructing an oracle with those matrices and -1 on given axis, and also how you can decompose this state into the matrix you want by using a single control Z gate. And this also is in a matrix representation of, this will be 0, 0, this is 1, 1, 1 is 1 for sure, 1, 2, 3, 4, 5, 4, 5, 6, sorry, 1, 2, 3, 4, 5, 6, 7, 8, -1 definitely here. And also this is the binary representation of I think, I'm not sure. This is no, this is 16 different. Sorry. Yeah, 8 or 16. 16 will be.
Oh, it is 8, right? 2 to the power 3.
Yeah, 8. 8. 8. It's 8. But this is maybe 2 to the first power. 0 power actually. 2 to the first and 2 to the second. So this is 4 plus 1, which is 5. So 0, 1, 2, 3, 4, 5. 1, 1. Once again, we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. So here is -1, and here's also -1. Am I right? No. 0, 1, 2, 3, 4, 5. Here should be minus sign. I'm sorry for that. Yeah, and this can be, as I said, implemented with simple control.
Can you tell us how did you do this trick to find where you should put the -1?
You mean this one here?
Yeah.
So yeah, this comes down to the binary representation of strings. So
okay.
Right. So this is 2 to, let's say, in the second position, right? Plus 2 to the first, plus 2 to the 0. And if it is, then you have to apply 1 times. Yeah, so this is 4 plus 2 plus 1, which is actually 7. But you start counting from 0. Right, so you have 0, 1, 2, 3, 4, 5, 6, 7.
Nice.
And this is again 5.
Okay, and this is in line with how you also give the name to each of the eigenstates. Like 0, 0, 0, 0, like all 0 is like the first
0
eigenstates, which is like 0 eigenstates. Okay, got it. Okay, nice.
Yeah, let's say yes. I mean, depending on what problem you're trying to solve, sometimes it's more convenient to use the binary representation. Sometimes it's more convenient to use a integer representation. And tomorrow we will do others and numbers checking. And actually, in our ThinkQubit Leap, when we are dealing with finance, actually, it's very convenient to use. No, it should be actually numbers checking. Other, yeah. So tomorrow I will very briefly show you this. No, it's maybe it's in finance. No, sorry. Maybe algorithms. Yeah. So actually, in our I cannot find this right now, but it's definitely somewhere here. 2-qubit gates. Maybe I deleted it. Never mind. But no, it's here. It's other. Never mind. So let's say in finance, we are, let's say, dealing with stock prices, which are floating point operators, right? So, but in quantum computer, we're dealing with bit strings in binary representation. So we actually can represent this as a floating point quantum number. This is like very, let's say, out of topic, but just wanted to show you that, yeah, you can represent also floats on quantum computer. And in some cases, like in our case for finance, this is very, very useful. Yeah, to represent it in either a integer representation or actually a float representation. I will maybe very briefly show you this on Friday, those codes, but it's not especially for QNickel course to do. Yeah, so I think for the assignments, I'm not sure if
will we have access to your like library, ThinkQubit library?
Yes, for sure.
Afterwards also?
Once again?
After the workshop?
No, unfortunately not. After the workshop, no. Yeah, this should be also. So I said that after the workshop, we will unfortunately cancel your access to ThinkQubit platform because it's still under development and let's say it's intellectual property. But you have the access to the platform as long as the assignments are due. So don't worry that you will lose access.
Okay, nice.
Yeah, lose access to the platform. but unfortunately the library is like private and it's not accessible in public. So you can, let's say, try to test those codes and play with them if you would like. There are different folders with math, quantum computing, also with this algorithms, the Grover algorithm we're covering, and the MaxCat problem also is there in the FinQubit library. We will like cover it briefly on Friday. But yeah, in the meantime, if you're interested, you can take a look at this. And also there are some algorithms from Qiskit Finance to calculate the price of an options, call option and put option. So if you're interested, you can feel free to go and execute those notebooks. They're in Julia, but we will work in Julia also, during Friday's lecture to implement the Grover for the MaxCat problem. But yeah, for today, I think it's it. For the assignments, you have introduction to Circ. And yeah, once again, there were some issues with the Python kernels for that. So actually, the notebooks were written in very old version of Qiskit, but the assignments are written in the newer version of Qiskit. So for the notebooks, I highly recommend for you to use. I highly recommend for where is it to use the QNickel kernel, Python kernel. But for the assignments, I recommend you to use the Python assignments kernel. And therefore, you should be able to no module name cert. Okay. So for the cert, you should use the QNickel. Or maybe I will try to fix this also tomorrow. Because for, yeah, I guess those were different. So once again, sorry. For cert assignments, you can also use the QNickel kernel. But for the assignments with Simon and classical gaze, you should use Python assignments kernel. I know it's unfortunately confusing, but due to like different version of Qiskit, I had to change the version and update the newer. But on the other hand, the notebooks were running in the old version. So yeah, this creates conflict. So yeah, to sum up, you should use Python assignments for assignments in Qiskit and use Python QNickel for assignments with Circ because Circ is installed in this kernel, and you should be fine. And I think you should be fine. So the questions are actually very simple. Applying the Hadamard and controlled Z gates. You have everything implemented in the notebooks and in the codes we use today. Yeah.
And
I think
sorry,
you should.
couple of us had an issue with the first assignment, classical gates, in a sense that it shows that from the first test we get 0 out of 2, and from the last part we get 6 out of 6. Can you also try to see if something, because it seems that something is not correct there.
Yes, I will try to find it, but unfortunately, I don't have access to the grading myself either.
But like at least you can check if you do the test correctly, as you know. If you get this and if you run it, you get the 0 out of 2, or you get 2 out of 2.
Yeah, sure. I will try to do this, but unfortunately, I also don't have access to these problems. Yeah, it seems like the problems at canvas level, not at notebook level. Yeah, I think so too. So yeah, we're really sorry for that, but well, the certificates are like we manually like do the certificates, let's say. So yeah, we will see if there's like few points missing, then you should be fine even with those assignments. Not
Maybe I
passing.
will add that one person from the Q Education department, Kenneth, who is responsible for Canvas, has already started investigating this case. We'll see. Maybe he will manage to fix the problem. He was also surprised that it happened because it didn't happen in the previous workshop. As you can see, this QNickel workshop has the number 26. So even as QPoland, we've already organized 2 or 3 QNickel workshops before, and we didn't have such an issue. So something changed. Probably something was changed. Kenneth is also not aware of the reason of the problem, but he has started investigating it, and hopefully we'll find a solution.
Thank you, Pavel.
Yeah. So yeah, I think this concludes today's lecture and session, and now we'll have your free time to complete the assignment with CERT, and also go through the notebook once again if you feel lost. Do you have any questions that I should revise, go through once again? I cannot see any hands. So once again, if you feel lost, you can also investigate this QBronze. And I strongly suggest you catch up with the Grover algorithm because understanding is crucial for solving the max-cut problem.
Oh, but
So
I just remember. So you mentioned at the beginning that, okay, for now, let's assume that we know the key.
yes,
What we build everything assuming that we know the key.
yes.
But like I thought that at the end you will cover that if we don't know the key, what will happen?
Yeah. So if you don't know the key, and if let's say if you don't know the key, then someone gives you the oracle. You don't have to implement the oracle. So one step is, let's say, away from you. I mean,
Oh,
one
but
second.
Somebody gives me a set of numbers like between 1 and 32, and he knows which number is the chosen one.
Yes, but they have to like provide you the oracle, right? So at the beginning, very beginning, we were investigating like such a black box, right? So you take a value, you don't know which one is the key. You go cross-check every single input and you go, aha, so 100 is a key. And similar to this, in Grover search, you don't know the oracle, what's inside the oracle before you run it. So that's why you need to like implement, let's say your task is only to implement the diffusion operator.
Oh, but then I don't know even how many keys I may have. So the point will be how many times I need to run, like how many times I need to do this.
I mean, you
right?
you should know how many keys there are because that determines how many times you run the algorithm. So you should know how many keys there are, and that there are, let's say, n different numbers you can choose from those keys to be. But for, like, say, our purpose to actually also implement this this oracle, we let's say we know which key we're looking for. So there are two different scenarios. One scenario is that someone gives us the oracle and says, find me the key. And we say, okay, we just run our Grover algorithm and find the key. In the second scenario, we are the one who provide the oracle to someone. And we say, here is your oracle. Try to find the key. And our task is now to implement this oracle that we will give to someone. Do you understand more or less?
Almost.
Can we also pass the key and stuck in a loop? I'm not sure what you're talking about. I mean, classically, yes, you would have to do it in a loop. Pass one value and another value and another value and do it n times. But in quantum computing, with the superposition, you can, let's say, create the superposition and feed all the numbers into the oracle at once. The question is how you then read the measurement. This is something different. That's why it's quadratic speed up, not exponential speed up, let's say. But yeah. Could you please share the link to bronze? Yes, for sure. This is just if you type Q bronze, Q world, you should be fine with searching that. But I can also provide you the link. Q bronze. No, sorry. Q bronze, but also GitLab. Yeah, maybe it's good to share this on Discord also, but maybe not in questions, but let's say important links, maybe, if Pavel allows me to.
Mm-hmm.
What is the ideal number of iterations to find the key? Yeah, so we discussed it earlier. So the ideal number of iterations is based on this angle theta, and this is, let's say, pi over 4 square root of n, but you know the pi is an irrational number, it's not an integer, so very often we do this like floor, so we round this number down. This means that if you see like something like, let's say 6.23 or even 94, you should round it down to 6. So you should do 6 iterations. And this is for the single Grover in the case when you have only one key. But in the case of multiple keys, then the answer is you should do it. Let me find it. You should do it 1 over square root of n over k times. And there's like some pi over 4 there also. Yeah, do you have any questions? Maybe you can elaborate on the question. Can we also pass the key and stack it in a loop? Because I'm not sure I understand correctly. Okay, if not, can more number of qubits increase the resolution? The more number of qubits increase, let's say, the available keys you have. So if you have, let's say 10 qubits, right? Then you can search, let's go back to our binary representation, right? So actually our, let's say, number 63 will be represented in binary as I think 1, 2, 3, 4, 5, 6, 7, 8 different bits, right? And let's say number 0 will be then 0, 1, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So the number of qubits increases like the maximum number you can represent, the maximum key you can have. And if you have, yeah, and this scales like 2 to the n of qubits. Do you understand? Have I explained it correctly?
Shouldn't we have 6 or 64?
64? Yeah, there's 64 number of combinations, but In binary, this is 63 because you count from 0.
No, I mean, shouldn't we have 6 positions, not 8?
It should be 8 times 6. Yes, right. Sorry. Yeah, of course. Yeah. You're right. I'm sorry. Yeah, because it's 1, 2, 3, 4, 5, 6. Yes. Because 2 to the 6 is 64.
So the number of qubits is related to, let's say, data set that we have. So if I'm looking within a data set which has 32, then I need 5 qubits. If I'm looking for in a data set which is 64 different values, then.
Yes, exactly. Does the final state always collapse to the key after proper number iteration? No, it collapses with a very, very high probability because even in the, I think there was something here. I will try to find this. Yes, this is it. So look, we have implemented our Grover algorithm with Hadamard gates Z, which is the oracle, and Grover diffusion operator. We did it 3 times because we have, this is the optimal number if we have 4 bits, but the measurement count is somehow different. So we get 111,900 times, but we have some also have some leftovers. So this does not mean that on every single execution we will get 111 100% of times. No, we will get 111 with a very, very, very high probability, and its probability is 95%. And the remaining percentage goes to some random bits. And this is due to the fact that if you, let's say, imagine going with the circle, going through this unit circle a few times with, let's say, some very odd number theta, which is like this pi over something, then you can sometimes overshoot your result or be a very, very, very close to your result, right? But it may happen that you will never be exactly aligned with this key vector. Because if you apply next iteration, then you will be somewhere here, right? So this line here is the probability of measuring other states than the key state. And this reflects itself in the fact that we have measured different bits a few times. So it is sensitive to number of iterations. Definitely yes. And we discussed that the optimal number of iterations is square root of n. Let's say pi over 4. Because if you do more iterations, then you will end up on the circle like somewhere here, and you will even maybe obtain some, you can even probably go back to your original state after more and more iterations. So that's why the optimal number is always this one.
And there is this one example with like 2 qubits that you can 100% get the correct one, right?
Your question, is it possible or?
Yeah. I mean, it's one example that like for the test that we have done for 4 qubits, if we do it for 2 qubits, what you have shown, it's like then we get 100%. So there are some cases that we may get like collapse to the key 100%.
Yeah, probably yes. Yeah. Probably yes. Yeah, I think it maybe if this square root is an integer. Right? If you have, let's say, a square root of 9, if it's n is 9,
Oh,
probably also, right? You mentioned n equals 4 or 2.
no, because I think that also because here you do the approximation to get it, right? You assume that sine of x is x. So this is not
okay. Yeah, maybe you're right.
So it's more like the theta that you calculated at the beginning. If it would be pi over 2 divided by an integer, then with the number of integers you will, or 2n plus integer.
Yeah. That's more plausible. Yeah, right. Yeah, that was my just intuition about it, but yeah, sometimes you can get exactly what rather often you do not.
So, but like in practice, is it possible to run and measure and see, like to keep running until my probability gets higher and higher, and as soon as it gets lower, I stop and I go back to the previous.
Yes, of course you can do it, but if your
like,
task
is
is
it
to
something
find,
practical or not really? If I
huh?
don't know, is it something practical if I don't know the number of keys? Or like in practice, maybe they do something else, that there's some more, smarter approaches if we don't know the number of keys.
Hard to say, to be honest. I'm not exactly, I mean, you say in practice, but actually the quantum computers are not even that good, let's say, to implement this Grover, let's say,
No, I mean at the
in practice.
theory, yeah, at the theory level, is it like, because like yesterday we learned from Lydia that there are some smarter approaches that for different, even like classical search problems, maybe there are some smarter approaches.
Yeah, if
That I'm
for
just
search problems, then she probably meant Grover.
Hmm.
But mm, hmm. I mean, theoretically you could do this, but if you didn't know the number of keys, but then let's say for each, to get a probability, you have to execute an algorithm, let's say 1,000 times, right? So now your complexity, let's say, increases, because now you have to check for every number of iteration whether your probability increases or decreases. So it's not efficient. Is it more efficient than Grover? We would have to like prove it mathematically. I'm not sure, to be honest, right now. But let's say it becomes less efficient because you have to first execute this square root of number of n times, and then you have to iterate it once again, probably times, I don't know, like some times n, probably like maybe some factor here. But I mean, you can see that this definitely increases complexity.
Okay, thanks.
Are there any more questions? If not, then I will thank you very much for today's lecture. And remember that tomorrow we are meeting at 1 hour later. Yeah, because I have exam also. Yeah, we'll see you 1 hour from 1 hour later than today. So in Poland, it's like 6 p.m. So it's on 7 p.m. and UTC 0 is 4, then on 5 p.m. UTC plus 0, right? Yeah. So thank you very much.
Thanks so much.
Thank you. Thanks, Krzysztof. I will now stop recording.
Thank you.
Dziękuję bardzo.